Hello everyone, greetings to all. I am Ezhilarasu, Assistant Professor, PG and Research Department of Physics, Bishop College. Today I am going to discuss about the nonlinear electronic circuits. In that nonlinear electronic circuits, I am going to discuss about the Chua's oscillator. So the Chua's oscillator is a simple nonlinear electronic circuit that exhibit chaos. This means roughly a non-periodic oscillator. It is unlike the linear oscillator. For example, Hartley oscillator, Colpit oscillator, and Weinbridge oscillator, phase shift oscillator. All these oscillators are linear oscillators, but this Chua's oscillator is a non-linear oscillator. It produces non-sinusoidal oscillations. This oscillator is invented by Leon Chua in the year 1983. So Chua's oscillator, in order to exhibit chaotic oscillation, the circuit needs at least 3 storage elements and at least one nonlinear element and at least one locally active resistor. In this Chua's oscillator, Chua's diode is being a nonlinear locally active resistor. So this satisfies the condition. Before going to the Chua's oscillator, we should know the fundamental circuit elements. So here we are using a resistor, capacitor, inductor are the basic passive components. So the resistors defined by the relation between the voltage and current. This is the symbol, and physical resistor is shown here. Then the relation is V is equal to R into I. That can be written as dV is equal to R into di. The inductor defined by relation between flux and the current. Here the physical inductor and symbol of the inductor is shown here, and pi is equal to Li. Then we can write d pi is equal to L di, or we can say V of t is equal to minus L di by dt. The minus sign is the opposing direction of the current. Then the capacitor is defined by the relation between the charge and the voltage. Here the physical capacitor and symbol of capacitor is shown here. The relation is Q is equal to CV, or we can write I of t is equal to C into dV by dt. And another important element is piecewise linear element. This circuit is the Chua's diode circuit. Here we are using 2 negative impedance converter connected in parallel. This one R1, R2, R3 is connected with one operation amplifier, that is one NIC, and R4, R5, R6, these connected with another operational amplifier 741. This is the second NIC. So we are connecting the 2 NICs in parallel. By using this circuit, we can get 2 negative slopes, GA and GB, that is defined by that by the equation shown here. The characteristics of this Chua's diode is shown here. We can observe 2 slopes. One is inner slope and another one is outer slope, and 2 positive slopes. Totally 5 segment piecewise linear element. The other graph is shown. We took the data from the lab and we plotted by our hand by taking the x-axis as voltage and y-axis in current. So then we plotted the graph. We got the experimental result is obeying the theory also. So the characteristic curves equation G of VR is equal to GB VR plus GB minus GA into E1. This is in this portion, negative portion, this negative portion, and GA into VR is the inner portion, and GB VR plus GA minus GB E1 is the this third quadrant portion. So this equation can be written as VR is equal to M naught VR plus half of M1 minus M naught VR modulus of VR plus BP minus VR minus BP. Then from this graph we can observe the slope of the two inner and outer slopes. M1 is M naught is equal to minus 0.409 millisiemen, and M1 is 0.756 millisiemen, and the break point is 1.08 volt. So this is the Chua's oscillator. In this oscillator we are using 4 passive component and 1 active component. The Chua's diode is the active component, and we are using L, C1, C2. These are the storage elements, these are the variables, and R is the control parameter. So by using Kirchhoff's voltage and current law, we can write down the equation. In this circuit we use this node and this node. This is C1 and this is C2. From this circuit, in this point we can write this equation: C1 dV1 by dt is equal to V2 minus V1 divided by R minus G of V. G of V is the current through this nonlinear element. Then second equation, the equation is taken here, the current through the capacitor C2. So C2 dV2 by dt is equal to V1 minus V2 divided by R plus IL. So these two equations are current equation, and the last equation is voltage equation. This loop L and C, this loop is used for voltage equation. Here L by dt is equal to minus V2. Then we can use this nonlinearity GV, we can fit into that equation. So we can find totally 3 coupled equation in this oscillator. From this oscillator, by doing the experiment in the laboratory, we can get the fixed point. By changing the R value, we can get the phase portrait of 1t, and you can observe this time series. We can find the amplitude all are same. In the second figure, the phase portrait gives the 2 limit cycle, and here we can find 2 different amplitudes. Here also we can find 2 different amplitudes. So therefore we are getting 2 limit cycle. Here we are getting 4 limit cycle, 4 different amplitudes. Then after tuning the resistor at one particular R value, we are getting 1 band bias. So the corresponding time series given here, and in order to confirm the chaotic oscillator, so this is the fast Fourier transformation. This gives the chaotic pattern. It is a wide band spectrum confirms this chaotic behavior. And again we are tuning the resistor, we are getting double band chaos. The corresponding time series and its FFT is given here. In the laboratory, we are using a breadboard. So this portion is nonlinear element, the Chua's diode, and this one are 2 capacitors, and inductor is connected with the use of inductance box, and this is the potentiometer. By tuning this potentiometer, we can observe the output. By seeing this video, we can observe 1t, 2T and 4T chaos, 4T, 1 band chaos, further increasing the resistor, 2 band chaos, and further increasing, it is keep on shrinking its area, and finally we are getting boundary condition. So this is the boundary condition. So we calculated and we observed the R values for the bifurcation sequence by reducing the variable resistor R. When I place 2K resistor, there I am getting DC equilibrium point. It is a fixed point, and if I keep 1.88 kilo ohms, I am getting period 1, 1.85 kilo ohm, I am getting period 2, 1.825, I am getting period 3 window, and 1.79 kilo ohm single scroll attractor, and 1.74 kilo ohm double scroll attractor, and 1.49 double scroll, again double scroll attractor, and 1.40 kilo ohm limit cycle is occurred. So this same equation, before we saw the electrical equation, the electrical equation is reduced and it is normalized in order to eliminate the units of the capacitor, resistor and inductor. So we are using this normalization terms. V1 is equal to x BP and V2 is equal to y BP. Like this, we are taking the variables and we are getting the equations. Dx by dt is equal to alpha y minus x minus h of x, and dy by dt is equal to x minus y plus z, and dz by dt is equal to minus beta y, and the nonlinear element h of x is equal to bx plus half of a minus b into modulus of x plus 1 minus modulus of x minus 1. So by using this normalized equation, we can use any software to get the solution. So we wrote in Fortran 95, from that we got the results. So this is 1T, this is 2T, this is 4T, and this one is single scroll attractor, double scroll attractor. So we observed the oscillations, and coming to the applications, this oscillator can be used in the secured communication and controlling the chaos. So if it is a control, if it is chaos is, can be controlled and it can be changed to a sinusoidal or some limit cycle oscillations, then it can be used for trajectory recognition via arrays and handwriting character recognition. These are the some applications. Thank you.